some months ago, and it's spin liquids and frustrated magnetism. So the plan for the 6 lectures that I'm going to give is over here. Today I'll start with an overview, and then I'll talk about classical ground state degeneracy in frustrated magnets, which is to do with how you destabilize conventional ordered states through frustration. And then I'll talk about one of the phenomena that can undermine this destabilization, which is something known as order by disorder, or ordering driven by fluctuations. Maybe some of you, when you read the term spin liquid, think immediately about quantum problems like the ones that Xiaogang Wen was discussing yesterday. But there's actually a great deal in frustrated magnetism that I think is very interesting, even at the classical level. And my second and third lectures will be about this interesting physics. And one title to put it under is what's come to be called Coulomb phases, because of certain special correlations that these systems have that I'll describe. But then in the second half of the course, I'll go on to talk about spin liquids, and in lectures 4 and 5, I aim to talk about spin liquids and quantum dimer models, and then in the final lecture, I'll try and wrap up and possibly talk about other viewpoints from the ones that I've focused on. As well as being given a title by the organizers, I also had strict instructions to arrive at the school with a draft of my lecture notes ready to be posted on the website, and sadly that hasn't happened yet. But there is some reading on the school webpage, some of which was suggested by me. And if you look at this collection of articles, then I think you'll get a reasonable summary of the things that I'm talking about. So there's a summer school article I wrote a few years ago. There's a research review by Castelnuovo, Mersner, Sondi. There's some summer school notes that Mersner and Raman wrote, and also 2 summer school articles, one by Gregoire Misquich and the other by Claire Huillier. Okay, so as I said, I want to start with an introduction, and let me begin by talking briefly about these 2 terms, spin liquids and frustrated magnetism. So obviously the term spin liquid is meant by analogy with the usual phases of matter. And it's easy to guess that in this analogy, the gas is supposed to correspond to a paramagnet, and the solid is supposed to correspond to something with conventional magnetic order, let's say a Néel state. So somehow the liquid, well, it might correspond to a classical spin liquid. And here classical, I just mean something that you can describe with a classical model, a classical Ising or possibly Heisenberg model. But the analogies, to my mind, are not all that good. The correspondence between a gas and a paramagnet is fine. This is something that happens at high temperature, and in both cases we're talking about something that's absolutely uncorrelated. And again, the correspondence between the solid and the Néel state is fine. It's at low temperature, and you have broken symmetry, so some conventional long-range order. But the things that make classical spin liquid worth studying features that you don't really have in conventional liquid, because in a conventional liquid you have really a short correlation length, and although correlations are strong on the atomic or molecular scale, they don't extend very far. Whereas in classical spin liquids, in the sense that I'll be talking about them, you have a correlation length that's parametrically large, and of course the parameter is the inverse temperature, and so what I mean here is that you can have a correlation length that diverges as you go to zero temperature, and it's the correlations within this correlation length that make the subject worth discussing. Of course, talking about phases of matter, we also have quantum liquids. And so we can think about quantum spin liquids over here. But again, I don't think the analogy is terribly good. If we're thinking about Fermi liquids, then the point is that if we consider a lattice spin system, we don't have anything like the Pauli exclusion principle to stabilize a liquid. If we're thinking about Bose liquids, then in the spin system, if we're searching for something that doesn't have conventional long-range order, what we want is precisely different from the Bose liquid. So the interesting things that are going to come out when we talk about quantum spin liquids... Sorry, I got this in the wrong column. This should have been over there, and this should have been there. The interesting thing that's going to come out when we talk about quantum spin liquids is that you can't have something that's completely disordered in a quantum ground state in a way that would be analogous to a paramagnet. Instead, as Xiaogang Wen was talking about, we're likely to have topological order. And emergence excitations, which are different from what you might have guessed at, knowing the degrees of freedom that go into the system. So then the other basic term to introduce is frustrated magnetism. So the materials that we'll be thinking about are Mott insulators, mostly good Mott insulators with well-defined local moments. And so we expect to describe them with simple models, Ising models, Heisenberg models, and so on. And the interesting thing about frustration is that it gives us a way of destabilizing conventional ordered states that you'd think of classically, like, for example, the Néel state. And there's a simple way of illustrating that, which I think is worth pointing out. We can think of a cluster of spins which are all antiferromagnetically coupled to each other. And to make it seem a bit general, we can talk about a cluster of Q spins. So if we had Q equals 2, it would just be a pair like that, but Q equals 3 would give us a triangle, and Q equals 4 would correspond to a tetrahedron. And we might also think about n-component spins. So if we write down a Hamiltonian that has all of the spins coupled to their neighbors, then we have something like that. And, I mean, of course, you'd normally exclude the terms when I is equal to j, but they're just constants, so it doesn't matter if we leave them in. And then we can also write this as the square plus a constant from the diagonal terms, because when you expand the square you get all the important off-diagonal terms, and this makes it clear that at the classical level we get ground states. We minimize the energy by making the total spin 0. So, to think about ground states, we should think about arrangements with 0 total spin on these different clusters, and if we just have a pair of spins, then it's obvious that the spin should be anti-parallel, and the degeneracy in the ground state is simply the degeneracy that comes from the global symmetry of the Hamiltonian under rotations. So there are no surprises in that first case, but when we go to larger numbers of spins in the cluster, then we can get degeneracies which are not a consequence of symmetry, and so in the technical sense they're accidental degeneracies. So if I focus just on this case with q equals 4 and think about two examples, if I take Ising spins, then to have net magnetization 0 for the cluster, I need 2 spins up and 2 spins down, but I can choose which spins are up and which spins are down as I like. So 4 choose 2 gives me 6 states. And if I think about the classical Heisenberg case, then I can kind of draw a picture of unit vectors arranged in space so as to have 0 resultant. And if I think about the number of ways of doing that, then clearly I've got some degeneracy from the global symmetry, from rotating any arrangement rigidly, but I've also got 2 internal degrees of freedom because I can change that angle, and although I've drawn the 4 spins in the plane, I'm not constrained to configurations like that. I can rotate this pair of spins relative to that pair around this axis. So in this case I have 2 degrees of freedom in addition to the ones which follow from the global symmetry. So the central idea is that this extra degeneracy helps to destabilize the ordered states. So now I want to show a certain amount of experimental data.
Question?
Yes?
Where did the accidental degeneracy come in?
Well, so in this Ising case, for example, the point is that by counting we have 6 states, but on the basis of the global symmetry, we might only have expected 2 states. So the extra factor of 3 is accidental. And I'm using accidental in a technical sense in which it's sometimes used in quantum mechanics when you talk about degeneracies which are not consequences of symmetry.
So which 2 states do we expect from symmetry?
Well, I mean, symmetry doesn't. Symmetry just gives us a total number. It doesn't privilege.
Sure. But I mean, yeah. Okay. It's okay.
Okay.
Yeah.
Right. So, are there any other questions whilst the projector warms up? Yeah.
You didn't mention the odd number of spinning clusters, which are frustrated intrinsically.
So you mean Q equals 3?
Yeah.
Sure, I didn't want to belabor the point. I thought that almost everyone would have seen a triangle with an upspin and a downspin and a question mark in the three corners. So I thought at least I could say something different. Was there a specific point that you wanted to bring out? Okay. Okay, so I wanted to spend a few minutes going through some experimental results on, I think it's 4 different materials. But before I do that, let me mention 2 lattices which will come up a lot in what we're talking about. So these are known as the Kagame and Pyrochlore, and as you see, they're built on these frustrated units that I was talking about, either by taking corner-sharing triangles or corner-sharing tetrahedra. Because this is obviously too complicated to draw on a blackboard, it's also useful to talk about a 2-dimensional version of this, which you can think of as a projection of one layer of tetrahedra, and I'll be drawing those pictures from time to time. Okay, so this is a list of the 4 materials which I chose rather arbitrarily to discuss. The first 2 are ones that we can probably think about purely in classical terms, and the second 2, the last 2, are ones where quantum effects dominate. Let me go through and point out the aspects of the materials that it's worth being aware of. So this first one I'm including partly because it was the material that really got interest in frustrated magnetism going in the late 80s, early 90s. The magnetic ions are chromium 3+. They have total orbital angular momentum 0. The magnetic moment is to do with the spin, and so you can think of them as Heisenberg moments, and you have a rather strong interaction. The scale is about 500 Kelvin, but nothing happens in the way of ordering down to temperatures of around 4 Kelvin. So clearly there's a wide temperature interval in which things are fluctuating strongly. It goes into a kind of spin glass state. I'll show a little bit of data on that. The second material, which I'll be talking about a lot in the third lecture, is something that's come to be known as spin ice. The magnetic moments are on these holmium ions, and they have both spin and orbital contributions to their moments, and then because of the crystal field, there's only 2 low-lying states, and so you end up with an effective Ising model. And the energy scale for interactions is rather weak, And this means that dipolar contributions are also important, and that turns out to lead to some very interesting physics. One difference which is significant for the data that I'm going to show is that this material is only available as powder, but this is available in single crystals which are big enough to do neutron diffraction from. And then there are these two materials with spin-a-half moments, in the one case on copper 2+, and in the other case in a singly occupied molecular orbital. And again, they have interaction energy scales of a few hundred Kelvin, but in fact they don't order down to the lowest temperatures that they've been studied. So let me show some of the things that you can learn from experiments on those materials, working through them in turn. So the simplest kind of measurement that you can make is of the magnetic susceptibility as a function of temperature, and this is data for this material SCGO. Of course, when you talk about real materials, there are often unwelcome features, and one of the unwelcome features here is that the magnetic ion sites are not always fully occupied, and so you have some dilution parameter, and these two curves are for different amounts of dilution. So when you think about what a susceptibility measurement like that teaches you, then you want to have in mind mean field theory, which for the susceptibility gives you the Curie-Weiss law, so that the temperature, the susceptibility goes as 1 over T minus some theta, which is positive in a ferromagnet and negative in an antiferromagnet. So what's plotted here is the inverse susceptibility as a function of temperature, and so the intercept gives you this Curie-Weiss constant, and you see that the intercept will be out at some negative temperature, so antiferromagnetic interactions on the scale of a few hundred Kelvin, depending on which of these two materials you take. And then if you focus in on what happens at very low temperatures, this time looking at the susceptibility, you see a difference between field-cooled and zero field-cooled susceptibilities corresponding to spin glass freezing at a temperature of 2 or 3 Kelvin. To find out more about what's going on in the material, you can look at spin correlations with neutron scattering, and these are the results for that same material. And you learn a couple of things. So first of all, there's a peak in the correlation function at a wave vector that corresponds to more or less the nearest neighbor spin separation. And secondly, there's rather little scattering at small angles. So the neutron scattering comes from fluctuations in the magnetization density, and what this is telling you is the fluctuations in the magnetization density are suppressed at small wave vectors, and that corresponds precisely to what I was discussing previously to do with the ground states of clusters being configurations with zero net magnetization. Okay, so those are comments on that material, and I'll go on next to spin ice. Any questions there?
So is it elastic scattering? Or?
Yeah, I forget whether it's elastic or energy integrated. I think at this temperature, most of the scattering is elastic. And there's probably some energy integration. So you should think of these as equal time correlations. Okay, so when we have single crystals available of materials, we can get much more detailed information from diffraction experiments. And these are some results from diffraction experiments on spin ice, which at the moment I'm not going to explain in any detail. They're kind of advert for the things that will be interesting in the second and third lectures. The basic point that I want to make at this stage is the results are quite different from the things that you learn about in elementary courses. So in an elementary course, you learn that if you have long-range order, then you can have Bragg peaks, delta functions, in the scattering response. And if you just have short-range correlations, then you can have some broad response in wave vector in the scattering. What we find here is that there are no Bragg peaks, but there are some very sharp structures in the scattering. So that tells us that we have correlations which must be long range in real space in order to give us a response that's sharp in wave vector. But despite being long range correlated, the system doesn't order. Then I'll go on to a couple of pieces of data from these two quantum systems. So first of all, this material that's known as Herbert-Smithite, which has spin-a-half moments on a Kagame lattice, and to a first approximation anyway, should be described by nearest neighbor Heisenberg model. And this is inelastic neutron scattering data taking slices at fixed energy in reciprocal space. And if you had an ordered system, then you'd have sharp response from spin wave excitations. And so these slices would be slices through the spin wave dispersion, and you'd only get high-intensity scattering corresponding to this red color on well-defined curves in the Briand zone. So the fact that the scattering is broad means that we don't have excitations of that type at all, and probably means that we have fractionalized excitations, although I must say there isn't a detailed understanding of this yet. And then the last experiment I wanted to talk about is on this organic material, where you only have tiny samples, so you can't do neutron scattering. But something that you can do is measure the heat capacity, and this is a plot, and the details are important. It's the heat capacity divided by temperature, plotted as a function of temperature squared. So the fact that we get a straight line with a non-zero intercept is telling us that the heat capacity goes like AT plus BT cubed, which of course is exactly what you have in a metal. And there you'd say that the T cubed is the phonons, and the T is from fermion excitations. But the point is that in this material, we have a good insulator, and so the fact that there's a non-zero intercept showing us that there's this linear contribution to the heat capacity is somehow presumably telling us that the spins are making a fermionic contribution to the heat capacity despite not being mobile. Okay, so any questions about any of that?
Well, to which extent the experiments you've chosen or believed to be universal because they are many compounds, and have you chosen this data because they are relatively generic, or well,
So I think they're intended to illustrate different aspects of the field. With the classical systems, I think we have a reasonable understanding of how to classify different materials and how the differences arise. And with these last two quantum examples, I don't think things are nearly so clear yet. And in any case, there are not yet as many well-studied instances. Okay, so what I want to do now is something analogous to what I talked about here, but at a slightly more serious level, in the sense that I want to talk about an entire lattice of spins rather than just an isolated cluster. And what I want to discuss is the ground state degeneracy for various examples. And I want to start with Ising spins on the pyrochlore lattice, this lattice of corner-sharing tetrahedra. And for this Ising case, there's an estimate of the ground state degeneracy, which I want to describe due to Pauling. So the first point is that the system has, well, of course, not a unique ground state, but in fact an extensive ground state entropy. And I suppose the first question is how you can see that. And to talk about that, let me draw this 2D version of the pyrochlore, where I'm thinking of projecting a layer of tetrahedra. So this represents 4 spins with interactions between every pair in the cluster, and then these clusters are corner sharing, so I have another cluster here but nothing here, and another cluster here, and so on. So if we pick a particular ground state which maybe looks like that, and then I could fill in the other spins, within that ground state we can find loops along which we have alternating up and down spins. So, for example, one of them is drawn like that. And so on every step of the loop, we have an upspin and a downspin, which are both part of the same tetrahedron. And so we can flip all the spins in the loop without changing the ground state condition that we have 2 upspins and 2 downspins in every tetrahedron. And then if we can find independent loops like this all over the lattice with a certain density, we can see that we can flip each of them independently, and therefore that we've got some positive rather than zero ground state entropy. So if you can convince yourself that you have a positive ground state entropy, the next question perhaps is, what is the, ground state entropy per spin? The next question is, what's its value? Presumably the exact answer to that question is something thoroughly non-trivial, but it turns out that this Pauling estimate, which I'm going to describe, gives you an answer which is good to within a few percent. So to make that estimate, we can start off by thinking about one tetrahedron. So altogether, because there are 4 rising spins and 2 configurations for each, we have 16 states. But of those 16 states, as we said earlier, 6 are ground states. So the fraction is 6 on 16. So if we go now to think about a whole lattice of n spins, and sometimes we're going to need to count spins, sometimes we need to count tetrahedra. So there are 4 spins in each tetrahedron, but each spin is shared between 2 tetrahedras, so if there are n spins, there are n over 2 tetrahedra. Then, for the whole lattice, the total number of states is 2 to the number of spins, and the estimate for the number of ground states should be that we should reduce this by a factor 6 over 16 for each tetrahedron. And since there are n over 2 tetrahedra, that's the reduction. So so if you combine these factors, then you get 3 over 2 to the number of tetrahedra. And so taking the log, we have ground state entropy per spin, which is kb over 2 from here, log of 3/2. And this is something that is shown up very nicely in experiment, and I'd like to show the experiment now, but I'm not sure how long it takes to turn the projector on. Okay, so in experiment, of course, you don't measure absolute values of entropy. What you can get is entropy differences by between two states by integrating the heat capacity divided by temperature with respect to temperature. So in a spin system with effective Ising degrees of freedom at high temperature, you know that the entropy should be log 2 per spin. And so if you measure the heat capacity going down in temperature, you can determine the low temperature heat capacity. And this is plotted, this is experimental data plotted as if the low temperature entropy were 0 and looking at how much entropy you recover going to high temperatures. And if you recovered the amount you'd naively expect, log 2 per spin, the curves would come up to here, but they're reduced by reasonably accurately this Pauling amount in the actual experimental data. And you can recover some of the missing entropy in an external field, although that's not something I want to go into now. Any questions about that?
Actually, a question about classical physics. It's a kind of a naive question. So we learn in elementary school that the third law of thermodynamics, the Nernst principle, say that the entropy must go to 0 when the temperature goes to 0.
Yes.
So how does it connect with this degeneracy?
Absolutely the right question. So, two things. In a theorist model, you can set things up so that you really do have non-zero entropy at 0 temperature, and this argument with flipping loops shows you how that can happen. But of course that's a theorist model, and one of the features that allowed us to have this entropy is that we had just nearest neighbor interactions, and for sure there are other interactions in the system, including, as I mentioned, dipolar interactions, which will give us a ground state that's unique up to global symmetries. So something that must be happening in experiment is that the system's not finding its ground state, and so in fact it's falling out of equilibrium at low temperatures. Okay, so that much obviously was in the language of Ising spins. You can ask similar questions about classical vector spins, such as in a Heisenberg model. But you can already see that the answer will be a bit different in detail, because whereas for Ising spins we simply count states, for vector spins we have a continuum of states. And so the question that we should be asking for vector spins is not what's the ground state entropy, but rather how many degrees of freedom are there in the ground state. And from that example of 4 Heisenberg spins interacting in a tetrahedron, we saw that there were, in that case, 2 internal degrees of freedom for the ground state, and we can ask that question more generally. There's a way of thinking about things that goes back to Maxwell of electromagnetism, who of course was thinking more about mechanical systems, I think kind of girder bridges rather than spins, but the same ideas work here. So the aim is to think about the number of degrees of freedom in the system, and then to think about the number of constraints which you need to apply if the system's to be in its ground state, and to ask about the difference between the number of degrees of freedom and the constraints, which you can then interpret as being the number of ground state degrees of freedom. So let's think about n-component spins in a lattice of corner sharing clusters of Q spins. So if I take the number of spins in a cluster to be 3, then an example of a corner sharing lattice would be this Kagame lattice. And if I take the number of spins in a cluster to be 4, then an example is the pyrochlore lattice of corner sharing tetrahedra. And the point about keeping things slightly general is to enable us to see what the overall pattern is. So if we ask about the number of degrees of freedom in the system, then if we have fixed length spins, then each spin has n-1 angular degrees of freedom. So the total number of spins is n-1. Sorry, the total number of degrees of freedom is n-1 times the number of spins. And if we have NC clusters, each cluster comes with Q spins, but they're shared between 2 clusters. So that's the number of degrees of freedom altogether. And then the constraints to be in a ground state. Well, from what I said when I was talking about a single cluster, to be in a ground state, if we have antiferromagnetic interactions within each of these clusters, we simply need to constrain the total magnetization of each of the clusters to be 0. So this constraint is, well, for each cluster we need to constrain each of these n components to be 0. So if we have NC clusters, that's the number of constraints. So what we expect is that the ground state degrees of freedom which I'll call D, F minus K, is, if we put everything together, we have something proportional to the lattice size, the number of clusters, and then n minus Q over 2, n minus 1. So if we think about Heisenberg spins, so n equals 3, on the pyrochlore lattice, taking Q equals 4, then this is 1, and we have number of ground state degrees of freedom, which is extensive, which is the analog for a system with continuous degrees of freedom to the extensive ground state entropy that we had for spin ice.
Isn't it off by a minus sign?
Have I? So, sorry, I've written things the wrong way around. Yep. So it's thank you. Yep, that's right. Yep, thank you. Okay, so you should probably stop there and worry about how reliable this argument is. And one point is that we've supposed that all of these constraints are linearly independent, and also that they can all be satisfied at once. And you can find examples where one or other of those things goes wrong. But for example, in this case of the Heisenberg-Pyraclaw model, this is essentially right in the sense that the corrections are of order 1 rather than proportional to the system size. Okay, so the picture at that stage is that because you have this extensive ground state degeneracy, or extensive number of degrees of freedom in the ground state, you've destabilized the long-range ordered Néel states that you might have in less frustrated antiferromagnets. But the fact that this degeneracy comes from is accidental rather than something arising from symmetry leads you to a problem straight away, which is that although you may have degeneracy in the ground state, it can easily happen that thermal fluctuations will lift the degeneracy and drive the system to order. And sometimes that happens, sometimes it doesn't. And I want to talk a bit now about how you decide whether it happens. So this is known as order by disorder. I think if we were inventing the term from fresh now, we'd probably call it fluctuation-driven order or something like that. And it goes back to Jacques Villain in 1980 and Eugene Schender in the early 80s. So the basic point is that the degeneracy is accidental, and if we try and picture things, then we can think of the classical phase space for the model, which of course is some very high dimensional space, and then we have some ground state manifold which I've argued is also very high dimensional, but not as high as the classical phase space. And then at low temperature, the system can access some region presumably close to the ground state manifold, but the fluctuations around the ground state manifold may be different in different places. So there may be some region where the system can fluctuate a lot, and other regions where it fluctuates less. So the basic question is, does the system maximize its entropy or minimize its free energy by exploring the whole of this ground state manifold, or by sticking in the vicinity of points where the fluctuations are softest and taking advantage of those soft fluctuations. So to think about that, at least schematically, we can imagine introducing some coordinates in phase space where we'll have some set of coordinates that take us around the ground state manifold. So this is a macroscopic number of coordinates, we've argued, and the remaining coordinates in phase space that take us off in the perpendicular direction. So if you think about doing the classical statistical mechanics of these fluctuations, then at least at some generic point in the manifold, you'd expect the energy cost of the fluctuation to be quadratic. So if you think about integrating over a single one of these coordinates, then you'd have some Boltzmann weight like that. And so this will give you something proportional to kT over the frequency square root. And so if you think about doing that for all of the transverse coordinates, you can imagine inducing a weight which will depend on where you are on the ground state manifold, which will come from doing all of these integrals weighted with whatever the full Hamiltonian is. And when we integrate over one coordinate, we get this with a square root, but presumably the coordinates will come in conjugate pairs, and so we'll get pairs of factors like this. And so the effect of doing this integral will be a product over modes, and for each pair of coordinates in a mode, we'll get a factor like that. But then the frequencies will depend on where we are on the ground state manifold. And the point is that if fluctuations are soft in some places, then the frequencies will be small. And in particular, it can turn out that the frequency for quadratic fluctuations can go to zero at particular points on the manifold. And if that happens, then that may drive the system towards order. Yes?
Why did you remove the square root between the two lines?
The details can depend on the system, but the most likely thing to happen is that you have a pair of conjugate coordinates in this transverse direction that make up the position and momentum of a harmonic oscillator. So taking them both together, you get two factors with a square root, and I was supposing that that's what happens. So the point is that the fluctuations may select states x where some of these omega L's vanish. And to see that, it's probably best to think about a couple of examples. So if I think about this example of 4 spins on a tetrahedron again, one ground state is one where the spins are collinear. And if I consider a small fluctuation away from that ground state, then, for instance, I can move those two spins like that through some angle delta theta. And,
Excuse me.
yeah,
What is exactly omega A of x?
so it's the coefficient in the quadratic energy cost of a fluctuation away from the ground state manifold. So the idea is that the energy is zero all around this ground state manifold, and it increases going away. And a reasonable assumption for a Taylor series expansion is that the leading term is quadratic in the displacement. So the omega is just the coefficient of that quadratic term. But of course it translates into the frequency for spin fluctuations if you think about dynamics.
There are cases where, let's say, the number of states where the fluctuations are slightly also macroscopically large.
Yes. Yes, I mean that has to be the case for something interesting to happen. If I have time, I'll talk about an example of that. Okay, so for this example, if we think about a fluctuation like this and ask what its effect on the total spin is, then the way I've tried to draw things, the component of total spin when we go to this state with a fluctuation in the vertical direction on the board is zero, but we have some resultant in the horizontal direction because these red spins no longer exactly cancel the bottom white pair. So we get a fluctuation in the total magnetization that's proportional to delta theta squared, and that means that the cost in energy of this fluctuation is proportional to delta theta to the fourth. Whereas if I take some more generic example, when I have four spins initially in a ground state, and then I consider a fluctuation delta theta like that, then in this case the change in total magnetization is linear in delta theta, and so if I put that into the energy, I get an energy cost that's proportional to delta theta squared. So the point is that some spin configurations can have soft fluctuations, and soft in the sense that the quadratic coefficient vanishes, and that will correspond to points on the ground state manifold where these frequencies vanish, and that may lead to those points being selected, and that will mean order in the system. And probably at this stage it's best to state the result for a couple of examples that we'll be interested in, and then I'll talk in a little more detail about how you can study that. So if we take the Heisenberg model, then on the pyrochlore lattice there's no order by disorder, so the system remains disordered, but on the Kagame there is order by disorder, which is basically the more soft modes in the sense I've been describing in the case of the Kagame than for the pyrochlore. Okay, I think the next thing that I'd like to do is, yes.
What your statement on the fiber of lattice is not a direct consequence of what you just said, because for frequency 4, you just showed that when these are collinear, you do.
Yeah. Okay. So the detailed arguments I don't propose to go through. What I want to do now is explain an exercise which I'd like to leave the students, which at least demonstrates a difference of this kind at the level of a single tetrahedron. To see these specific results, I'm afraid you need to go back to the literature. So I want to take a single tetrahedron with an energy which is the form that we've been talking about. And the spins, it's useful to have two contrasting situations to think about either XY or Heisenberg spins, and what I want to consider is configurations like this, where I'll think about two of the spins as being fixed and then integrate with a thermal weight over configurations for the other two spins. And the thing to specify about the configuration of the two fixed spins is their relative angle. And so I can think of kind of partial partition function, which is what I get when I integrate over the orientations of the two free spins. And then what I'd like to ask about is the probability distribution of this angle, or the weight on different values of the angle. So that'll be proportional to this partition function. And then, of course, it'll come with a measure. So if I've got Heisenberg spins, then we have a weight sine alpha coming with that angle. And if I've got XY spins, then there's just a trivial factor of 1. And the exercise is basically to find the form of this partition function in the low temperature limit. And what you should find is that the proportionality constants don't matter, but we have either sine alpha over 2 or 1 over sine alpha, according to whether we've got Heisenberg or XY spins. So what this result is telling you then is that for XY spins, the weight is divergent when alpha goes to 0 or pi. In other words, when the spins are exactly collinear or exactly oppositely directed. And so in the low temperature limit, fluctuations will drive a set of 4 spins with antiferromagnetic interactions on a tetrahedron into a collinear state if they're XY spins. But if they're Heisenberg spins, then this weight is pretty innocuous. All different orientations are possible, even in the low temperature limit. And this illustrates the difference that can come up, well, in this case, with the number of spin components, but also according to which lattice you study. Any questions about that?
Question. Well, this drawing of that, I don't understand why there would be regions where fluctuations are wider.
Well, that's the kind of thing that I was trying to explain with this example of fluctuations starting from a collinear state. So the point is that if this spin fluctuates up like that and this fluctuates in the opposite direction, then if we think about the total spin for this cluster, the component in the vertical direction on the board remains 0, and the component in the horizontal direction, the change in the total spin, is proportional to delta theta squared. And then because the energy is the square of this, it's quartic in the displacement, which is the soft mode that I'm focusing on. Well, that would be a possibility, but it's somehow off in a different area of theory from what we're focusing on here, which is whether the degeneracy that we hope will promote large fluctuations and destroy order, it's whether that degeneracy is strong enough to survive fluctuations. Thank you. That would really mess up the exercise.
So if the system is ordered by disorder, then does this make it extra hard to probe it? Because the fluctuation around that one is extra large compared to the
Well, I'm not sure that's necessarily true. I mean, hopefully that might make the fluctuations characteristic in some way. You can ask a similar question, which is, how easy is it to identify this kind of fluctuation-driven order in an experiment? And the difficulty then is that you're usually wanting to compare two possibilities. One is that you have a nearest neighbor model with this interesting large accidental degeneracy that we've been talking about, and the order which is observed is driven by fluctuations. But another more prosaic possibility would be that as well as the, say, nearest neighbor interactions, you have some further neighbor interactions which select the ordered state in a completely conventional way. So the difficulty experimentally is usually to show that the mechanism for ordering is fluctuation driven. But there are some examples where people believe this has been done.
Can you have a degeneracy remaining even after order disorder? Like you can have 2 points in your phase space which show similar order fluctuations?
Yeah, well, something that's very common is that fluctuations select some subset of states, but even within that subset, there's macroscopic degeneracy, and probably that's also lifted, but at some higher order.
So you go to the first excited state, look at what kind of states that's connected to, and then do the hierarchy of this? select this among this?
Yeah, I mean, as a comment, when you talk about things like first excited state and so on, it's not clear that that's the right language to be using, because at least at this level we're discussing a classical problem. So an example where the type of thing that we're talking about now comes up is in fact with the Heisenberg model on the Kagame lattice, where the leading effect of fluctuations is to drive the system into a state where all the spins lie in the same plane in spin space. But then it turns out there's still a discrete macroscopic degeneracy within that set of states, which is probably also lifted by fluctuations, but in a more subtle way. Okay, so I think I'll just take a few minutes to say a little bit about fluctuation-driven order in this same language, but now for a quantum problem. So if we try to use this picture, but for a quantum problem, then it's natural that we should be thinking about a semi-classical limit, which of course we can get for Heisenberg spins by going to large spin. Then the fluctuations which I was talking about in thermal language here will become 0-point fluctuations in the quantum case. So we'll have a set of finite frequency fluctuations characterized by these same frequencies, but the values of those frequencies will depend on where you are on the ground state manifold. So we can think of an effective Hamiltonian for the ground state coordinates which is just the 0-point energy of these fluctuations out of the ground state. So these coordinates within the ground state manifold will consist of lots of conjugate pairs, analogous to generalized position and momentum. So in the quantum problem, there'll be 0-point fluctuations within the ground state manifold, or quantum uncertainty in the values of those pairs. And the size of the 0-point fluctuations in these coordinates within the ground state manifold are determined by the size of the spin. So the idea is that you have some kind of Hamiltonian over this ground state manifold, which will vary according to the local value of the sum of the frequencies of the finite frequency modes. And if you thought about it purely classically, then the ground state that would be selected would be the one where the sum of these finite frequency 0-point fluctuations is minimized. But the 0-point fluctuations in the transverse coordinates may delocalize the system over the whole of the ground state manifold if S is small enough. So for large S, you expect order at some x equals x naught, which is the place where this effective Hamiltonian is minimized. But for small s, there's a possibility that fluctuations will delocalize you over this ground state manifold. Well, if you think of some familiar example, then, if you think of a single spin problem, say a spin in an external field or something, you can think about states on the block sphere, classically, you have all orientations distinct, but quantum mechanically you have 2s plus 1 states, and so you somehow think of 0-point fluctuations as delocalizing the spin over patches on the surface of size of order 1 over s. So when s is large, we can localize the spins rather precisely, and so we can take advantage of some minimum in this effective Hamiltonian. But if s is small, then it's harder for that to happen. I think in broad terms it's a correct picture, but it's hard to make it more precise than I'm doing now. But,
how robust is the expression for the 0-point motion energy? Because you took the expression from the harmonic oscillator. But if we think of a ferromagnet, in this case, there is no quantum correction to the energy. So, because you could have massive modes, but they don't give any correction to the classical estimate of the energy. For antiferromagnets, I think your formula is totally safe. Mm-hmm. If you have a kind of system that is between, that is neither ferromagnet nor antiferromagnetic, which is the case when you have these degenerate manifolds, how sure are we that this is the correct expression for the 0-point energy?
I think the ferromagnet is the unique special case, but
I agree that you need some fine-tuning to have the coefficient to be 0, but for this value 1/2, I'm not sure that it is.
Yeah, that may be the case. Yeah.
X,
yes. Yes. Okay, so I'd like to finish this lecture there.